Hi everyone, hope you guys are doing really good. Today we are going to discuss different schemes to represent systems. Up until now we have seen only one of those, that is the differential equations. But obviously there are other ways to define systems. We will see that today. Not only that, we will find ways to transform one representation scheme to the other. And that is going to be one major part of today's lecture. So let's start the discussion. But before we proceed, we have to answer this very important question, that why do we need those many different representation schemes? Can't we only use the differential equation that we have derived already? Yes, we can use that differential equation, but sometimes the nature of analysis would be different, and that would warrant a different kind of understanding or representation scheme. Let's have one example. For example, you have a system defined, and this system was, as we have said earlier, is going to receive the inputs and it is going to generate the outputs in order to interact with the environment, obviously. So if we are interested in finding a relationship between output over input, in that particular scenario, we would probably be needing a different kind of representation scheme that generally we call a transfer function approach. And in transfer function approach, you would see that there are some other benefits. For example, it is going to give you the characteristic equation that we can plot on an S-plane. This S-plane is going to have the real axis and the imaginary axis. And if we place poles over it, we are going to have a commentary on the stability of the system and the behavior of the system if certain parameter is changed. And that is going to be an important aspect to be considered in order to understand the stability and behavioral analysis. So on the left side, you are going to have the stable region, and on the right hand side, you're going to have the unstable region. And that is when you plot the characteristic equation or roots of the characteristic equation on an S-plane. So in that particular scenario, a relationship between output and input would be an important tool to have to understand the behavior of the system. But sometimes you would be interested in defining the system in a way that you have the states of the system defined. For example, for a dynamical system, you would be interested in the position, in velocity, and in acceleration, for example. If these are the states that you are interested in, you would be more interested in finding a representation scheme which gives you more insights. So in that particular scenario, probably the state space representation would be more appropriate. We will see that later on, but that is going to give you quite a few tools to identify the behavior of the system. And in addition to that, you can use the concepts of linear algebra or linear system theory on it more appropriately. And in terms of control systems, for example, you can make use of these concepts to define, let's say, for example, a good controller, like a full state feedback controller, can be defined very easily. You can have all those analysis of controllability and observability and all the relevant stuff done using this state space representation. So modern control system paradigm is more in line with state space representation. So that would be a good tool to have in terms of representing a particular system. But in certain cases, you would be interested in more like in a graphical approach to define your systems. Probably you can have a system defined like a block diagram. So if system is taking certain inputs and generating an output, you would be interested in taking this output from here and providing like a feedback signal to a feedback controller. And actually the feedback controller uses this error signal when it compares the reference signal coming in from this side with the feedback signal coming in from the sensory uh, arrangement. And that error signal is what is used in the control scheme to drive the system in a much more efficient manner. So in that particular scenario, you would be more interested in how the signals are correlated with each other, how things are schematically structured uh, in order to get more insight or more handy tools to define a good control system. So in that sense, you would need certain graphical methods oftentimes and some analytical methods like transfer function approach or state space representation scheme in order to have uh, a better understanding of the system. And in order to define the subsequent steps like control system definitions and all in a much more better way. So for that reason, I can now say with more confidence that yes, we need different representation schemes and that are going to be probably much more handy to perform certain aspects or certain analysis on the systems. So let's proceed with that. So in this context, we have two different paradigms to represent systems. One what we call mathematical and the other what we call graphical approach. In mathematical approach, you have seen the differential equations. You know now the state space representation is going to be needed, and oftentimes we would be interested in how the outputs and inputs are correlated and understand the characteristic equations. And similarly, in the graphical approach, we would love to have block diagrams, which are going to give us a visual tool to understand the systems. And similarly, we have a slightly modified graphical approach, what we call signal flow graphs. We may have other approaches as well, but we would probably discuss it later on, just like the bond graph methods. And then we have to have some sort of conversion tools to convert from one paradigm to the other, from differential equations to the state space representation, from here to the transfer functions, from transfer functions to the differential equations. We would love to have certain conversion approaches. And similarly, for the graphical paradigm, we would love to have the approaches to convert block diagrams into signal flow graphs and vice versa. And so on and so forth. We would also love to have certain tools where we can transform from the mathematical paradigms to the graphical and from graphical to the mathematical approaches. And these tools are going to help us out to understand and apply all those tools which are possible to understand these systems better, analyze them better, and improve the performance. So that's why these are going to be very important tools for the control system development. Let's now discuss the mathematical paradigm first, and in that we have the three topics to be covered. So first of all, we will see the differential equations. In previous lectures, we have seen a wide variety of differential equations. We started from the translational mechanical systems, and then we shifted on to the rotational mechanical systems. And then we shifted our focus on to the electrical systems where passive and active systems were discussed. And then we moved on to the fluidic systems. But more recently, we have seen thermal systems. And in that, if you recall correctly, we have seen this equation, and that was corresponding to the room heater example. So in that case, the heater was providing the heat, and as a result of that, the temperature of the room was getting raised, as well as it was changing. So this time rate of change of temperature was important, and how it is getting transferred out of the room as well. So you can see that this is a first order differential equation. And that order is defined by observing the highest order term of the time derivative involved in there. Similarly, you saw another example that was corresponding to, if I recall correctly, this was a water heater example. So in that case, you can see that the electrical power was given to it. So this electrical power was provided, and the water was getting heated. And in that case, you can see that the highest order differential term is first order. So that's why you can say that it is also a first order differential equation. Moving on, there was another example corresponding to a thermometer, and that was a second order differential equation because the highest order term was of second order. So this is the thermometer. You can see the second order term provided over there, first order term provided over there. So that's why it is a second order differential equation. And in that case, you can see that the temperature of the mercury was getting raised using this equation when temperature in the environment was provided as the input to the thermometer. And in the last lecture, you can see that you can recall that there was this armature controlled DC motor discussed, and that was having the third order differential equation. So this is the armature controlled DC motor model. And in that case, you can see that the input voltage is provided, and you can see how the kinematics of the motor are changing. And the highest term is the third order term, so that's why it is the third order differential equation. And on top of that, you can see that these equations were ordinary differential equations because there was no partial derivative involved. So that's why I'm going to use the word ODE, which stands for ordinary differential equation. So these are first order ordinary differential equations, the first two. The third one is the second order differential equation, ordinary differential equation, and the last one is the third order ordinary differential equation. These are linear as well. Since we have to use eventually the linear system theory, and we have to take the Laplace transformations and all that. So for that reason, we are going to limit ourselves to the linear models. So in this continuation, I can see that you are going to have a differential equation defining how the variable of interest is changing with time, and that is going to define how the dynamics of the system are going to change. So generally speaking, you are going to have one generic expression. So this is going to be something like this, that generally you are going to find out nth order differential equation in which you have something on the input given to it. I will write that later on, but that is going to be equal to, if it is the nth order differential equation in a generic form, it is going to be dn of x, which is the function or variable of interest with respect to time, dtn, then added with another term where you have the reducing order. So this is going to be dn minus 1 by dtn minus 1 of x. And since you are going to have a coefficient as well, so to be consistent with the notation that we have used, I can label it to be a n minus 1. Similarly, you can add a n minus 2 dn minus 2 by dt n minus 2 of x, and then you can have this whole continuation all up to the point where you have a1 d by dt of x, and then you have added with that a naught of x. And that is going to be equal to the input given to the system. So in that case, maybe it is changing with time, so that is going to be a function given to it. So you can see in this particular scenario that you have, let me encapsulate that as well, that you have an nth order differential equation, ordinary differential equation, and it is going to require n initial conditions given to it in order to have a solution possible. So generally speaking, you are going to have for dynamic systems such kind of representation where you have derivative terms. The highest term is going to define what is going to be the order of the ODE. We are going to limit ourselves to the linear systems, and we are going to keep them in that sense ordinary as well. In that sense, it is going to define how system behaves when certain input is given to it. The second type of representation scheme in this domain is called state space representation. And it is actually a slightly modified version of the differential equations. The difference is quite simple. In case of differential equation, you have the nth order differential equation. Which in this particular paradigm is resolved into n first order differential equations. And in most of these cases, you can do that by inspection. So in that sense, you have generally a single equation on this side that is transformed into n equations. How we are going to do that, that is the discussion that we will complete today. But actually, in terms of the difference, it is that simple, that you have to take the differential equation and by inspection transform into n first order differential equations. So when you transform it into n differential equations, you are going to have state variables. So this is going to define n state variables. And these state variables are the reason why we call this as state space representation. And on top of that, you are going to have two types of equations using state variables. One, what we call the dynamic equation or state dynamic equation. And the other one, what we call the output equation. We will see that in the next slide, but that is an important point to make, that we are going to use this representation scheme to define two types of equations. One, what defines the dynamics of the system, and the other one which defines the output of the system. How it is structured, let's see that. So if we define states as x, so this x can be n by 1 sized vector, or this is going to be called state vector. We will use that. Similarly, you are going to require the definition of inputs as well. So we are going to generally define it in terms of u, and that is going to have, let's say, r by 1 size. So these are the input vectors. And similarly, you are going to require the outputs. So this output is labeled as generally y in a generic notation, and this is going to have m by 1 vector. So this is going to be the output vector. So in that sense, you have n states, r inputs, and m outputs. So we are going to use these three vectors in terms of defining the state space. But the issue is that you may have the nonlinear and linear state space representation. So for nonlinear, you are going to define it like this, that the dynamic equation is going to be x dot, which is going to be a vector of the first derivatives of the states, to be equal to a function which takes into account the vector x, the vector u, and obviously it is time dependent, so I'm going to write that one down as well. So this is going to be the dynamic equation, and the output equation is going to be y, which is going to be equal to another function on the state variables x, u, and obviously these are going to be dependent on time. So these are going to be the two equations. This is the dynamics, state dynamics, and this is going to be the output. Now this is the case of nonlinear state space representation, but generally we are going to limit ourselves to the linear systems, as we have mentioned earlier as well. So for linear systems, you are going to have a slightly modified version of the state space representation, and that defines something like this, that you have x dot. Let me use a different color over here. So x dot is going to be equal to a matrix A times the state variables added with another matrix B times the inputs. So this is going to be the state dynamics, and I'll further define it later on. And the output equation is going to be something like y is going to be equal to a matrix C times the state variables x plus another matrix D times the input vector u. And I'm going to write this one down in terms of their names. So this A is called state coefficient matrix. This is going to be dependent on all these coefficients which define the internal nature of the system. Like for a spring mass damper system, it is going to account for the mass and the spring stiffness and the damping coefficient. B is going to be a matrix which is going to be called input matrix, because it is getting multiplied with the input vector as well. So that's also the reason why we call this as input matrix. C on the other side is going to be called the output matrix. And D, because you can see the inputs U are directly being fed to the outputs Y, so that's why it is called feed forward matrix. Now in terms of their sizes, I can make a realization now that if x is an n vector, you are going to have x dot to be n vector as well. So this is going to be, I'm using a different color, this is going to be n by 1 as well, because x is n by 1. And if u is r by 1, you can see that this is going to be having an effect on the size of B, and B is going to be in that sense n by r sized, and similarly A is going to be n by n. In order to produce the x dots to be n by 1 vector, you have to be consistent in terms of their sizes. And similarly for the outputs as well, you can define that if outputs are defined to be m by 1 vector earlier, so this is defined to have a size m by 1. So when x is going to be n by 1, you are going to define C to be having a size of m by n. And similarly for D, you can define that this is going to be m by r, where u is r by 1. So this is kind of the size realization of all these vectors and matrices involved in the system. So in a nutshell, for a linear system, I'm going to rewrite this equation once more. X dot, which is the time rate of change of state variables, is going to be equal to a matrix A, which we call state coefficient matrix, which is going to take into account all the internal uh, nature or behavior of the system or system components, times the state variables x, the vector of state variables, plus the input matrix B multiplied with the inputs given to the system. And you are going to produce an output or analyze an output in that sense that y, which is the output vector, is going to be equal to c times x, which is the output matrix multiplied with the state variables added with the feed forward matrix D multiplied with the input vector u. So this is going to be the output equation. So this defines a system in a very structured and methodical fashion where you have n first order differential equations defining all these states in it, and that's why it is called state space representation scheme. You should also take an additional note, that is that for systems which are time varying systems or time variants, you are going to have these matrices A, B, C, and D to be varying with time as well. And for time invariant systems, let me use a different color. These matrices A, B, C, and D are going to be constants. One simple example for the time varying system can be like you have a spraying drone, for example, which is spraying over uh, an agricultural field, and when it sprays, the quantity of spray is going to get reduced, so the total mass that it handles is going to grow smaller. So this is going to change with time, so it is a time varying system. And for time invariant systems, just like the spring mass damper system, the spring and the uh, uh, damping coefficient and the mass remains constant whenever you move it. So that is one example, simple example of time invariant systems. So kindly keep a note of that. Transfer function is the third type of mathematical representation scheme, and a very important one because we are going to frequently use it in the classical controls. So if you recall, we have just mentioned that it is going to be a ratio between the output and the input. But this definition is incomplete because these outputs and inputs are needed to be defined in the Laplace transformation. So it is going to be in the S domain. So at this particular stage, I'll take one step back and make you recall that the Laplace transformation was doing one very important transformation. In the time domain, we define systems having time as the independent variable. But what Laplace transformation does, it takes the system from time domain to the frequency domain or complex domain. So this is what happens with the Laplace transformation. But when we do that, the differential equations are transformed into algebraic equation, and that is the benefit of taking the Laplace transformation. So I'm going to write that one down, that this is going to take into account the differential equations, which are obviously dependent on time, into algebraic equations when we take the Laplace transformations. And that's why the handling of the system in the frequency domain is going to become much more easier, and a different set of insights can be developed over there. So the transfer function, the paradigm requests the designers to account for the Laplace transformations when it requires outputs and inputs. So that is going to be a ratio of the Laplace transformation of the output over the Laplace transformation of the input. And that can be if output is defined in terms of, let's say, Q. So this is going to be Q of S over if input is defined in terms of U, something like that. And that is going to be giving you a representation scheme where you have the numerator in the S domain over denominator in the S domain. And this denominator was defined earlier that if denominator is equated of a system is equated to 0, that is defined as the characteristic equation. And that is an important equation to analyze the behavior of the system. Now coming back to the point, when you have the ratio of the output over the input, that is going to define how the signals are transformed or transferred, and that's why the term transfer function is used. In addition to that, in addition to realizing that you are going to use Laplace transformations, you have to make sure that you account for zero initial conditions as well. Now, someone may raise this question that why we are going to have zero initial conditions, because system may not start from a set of zero initial conditions. So actually, if you recall that it is a linear system that we are handling, and in that case, the principle of superposition was applicable, which said that you can have two things separately handled. One where you have the response corresponding to initial conditions, separately handled, and the response that you are going to get in terms of input given to it and then you can have them added together because it is the linear system. You can have the principle of superposition accomplished to find out the total response. Actually, you have used that in order to solve the differential equations as well, but we're going to make sure that you correlate this principle of superposition in terms of having the transfer function constructed with zero initial conditions. Eventually, we're going to make use of the solution that we get or transfer function that we use over here alongside the response that we will get with zero initial conditions, and then we can combine them together. Coming back to the Laplace transformation, I should also emphasize that in the time domain, for example, if we are going to use the d by dt operator, the differential operator, that is going to be transformed into the S operator, and that's because the Laplace transformation has been taken over here. And similarly, if you have the integral, like integral of a certain function, when you take the Laplace transformation, this is going to be 1 over S in the frequency domain or in the complex domain. So we will use these kind of notations in order to construct the transfer functions. And these are going to greatly help us in order to understand how system behaves, how it handles the input and generates an output. In the subsequent discussions, we will also see how we're going to make use of transfer functions in order to understand the behavior of the system, in addition to finding ways to compute or construct the transfer functions so that we can later use them as well. Now we have covered the mathematical expressions, the one paradigm of system representation. The other paradigm is corresponding to the graphical representation. And in that, we have already mentioned that you're going to have two major categories defined over here, although there are other ways, uh, such as bond graphs, but we are going to focus currently on block diagrams and signal flow graphs. Now, in the very starting phase, we said that in a block diagram arrangement, you can have the block of a system defined like this, which receives the input or input signal and generates an output. Now, this is also consistent with the transfer function approach that we have just mentioned. So that's why you're going to frequently find the block diagram representation alongside the transfer function approach. So system receives a signal in terms of input signal and generates an output signal. And in that transformation, it actually behaves according to its own internal nature. If it is a spring mass damper system, for example, the spring stiffness, the damping coefficient, and the mass is going to define how system behaves in transferring the input to the output. Now, in case of control systems, what happens is that we take this information from the output and we provide a feedback. So in that case, you may have some sort of a transformation of this feedback signal, and that is transformed back to a summing junction where you compare the signals. So in that case, the comparison is going to be done with the reference signal. So this is generally done in a subtraction manner. So reference minus the feedback that you get out of your sensor model. And then you provide the error signal to the controller generally. And that is the general way of defining a control system. Now, in this particular realization that you can see that you have a graphical representation which gives you better insights of how you're going to connect the things together. But at this particular stage, I should emphasize that you need to realize what are the ingredients. So let me write those one down. So one ingredient that you can see is what we call the summing junction. And this is this round block. So you can see that the signal gets in there and also gets in there, and it produces an output signal. So this is going to be summing these two signals up. So if this is A in the frequency domain, for example, and if it is B in the frequency domain, you can have this to be A of S if it is the positive sign, and if it is with the positive sign as well, plus B of S. And if you add something in addition to that, let me use a different color. Let it be like another signal given to it, C of S, but with a negative sign. So you are going to get minus C of S as the output as well. So summing junction is going to account for all the signals from different sides, and it is going to sum them up and provide you the resultant signal. So this is one of the ingredients. The second ingredient can be the block itself. So this block can have a simple realization, for example, simple gain block, for example. And that would look something like this, that you have this rectangular block, but in that you have some sort of gain given to it. So in that sense, what happens is that whatever is the signal given to it, let it be like X in the time domain is given to it. It produces an output by multiplying this gain K with that. So this is going to be K times X of t. So this is a simple gain block, which, for example, if you have used the operational amplifier in your control system, that is going to have a simple proportional gain multiplied with the input given to it. So that would be in a block diagram represented in this fashion. And you may have a bit of complex uh, blocks, for example. Let it be like transfer function block. Now, in that case, for example, you can have a transfer function given to it. Let it be like g of s, and I'm using the s as because it is the complex number in there. Because in transfer function, you have just seen that you have to take the Laplace transformation of it. So in that case, what happens is that whatever is the signal given to it, if it is the input signal, and I'm using capital X because it is in the Laplace domain, so that is going to be g of s, x of s as the output. But this g of s can be of complex nature as well. So for example, in case of motor control, you are going to have the electrical part as well as mechanical part given as g of s altogether in it. So that is going to define how the output is generated out of that particular part. So this is going to be the second ingredient of the block diagram. And, and one particular block which is going to be an important block to be registered is what we call integrator block. And that is something like you have, for example, Sx, let me correct it, Sx of s given to it. So integrated block is going to be 1 over s, and that is going to produce x of s. In time domain, you can also write that one down. So this is in the complex domain. So in time domain, you can define in a simpler fashion like that, that you have x dot of t, and then you have the integrator block, which is going to be integral dt kind of arrangement. So this is going to give you x of t as the output. So we are going to make use of integrated blocks. We're going to make use of general blocks, which are going to have the gain block as well as the transfer function block. And we are going to make use of the summing junctions to construct the block diagrams. And we will see that later on that we can have a complex system constructed in a graphical way, and that is going to provide us how things are correlated with each other, how these can be cascaded in terms of control systems, how control system architecture can be constructed. And that's why this graphical approach is going to be much more helpful in the control system designs. Oftentimes, it becomes difficult to construct systems transfer function using the block diagrams. So it would be generally advisable to have a signal flow graph constructed first, and that is another representation scheme. So in that case, what happens is that you have nodes. These nodes are going to be connected with each other using the signal flows. So if nothing is happening, you're just going to place a 1 gain over there. But if gain is provided, you can provide that gain transfer function in that. For example, if you have, let's say, integration done, you can add that as well, and so on and so forth. And then you can place the loops as well. I'm just randomly constructing them. It is not going to make something like a particular sense in this case, just to give you an idea that you can have a feed forward arrangement, you can have the feedback arrangement, and that is going to be corresponding to the gains that you can provide. Let's say it is with the negative A gain, and this is with the positive B gain, something like that. And in that sense, you can start from the input node and you can go all the way to the output node, and then you can construct the transfer function which obviously is output over input, uh, using a specific formula, and that formula is called Mason's formula or Mason's rule. We will study that later on, and that would be very interesting exercise to transform the graphical representation into a transfer function which we can further analyze to get deeper insights of the system. So at this particular stage, we can say that we have covered the graphical approach as well, in which the block diagrams and the signal flow graphs have been introduced, but how these are converted from one to the other, this is yet to be seen, and we will see that in the next slides. So let's start with a very simple, straightforward example. So this is a very simple case. We will do more complex cases later on. So in this particular example, you can recall that we mentioned this thing earlier, that you have this kind of surface over which the spring mass damper system is placed. So this was something like structured earlier, like having a spring with a stiffness K and having a damper with damping coefficient B connected with a mass. This mass was able to move over this horizontal surface, and that was defined in terms of the variable or the coordinate system. Now also we ensured that last time the applied force was acting on it as well. So from here all the way to the constructing the free body diagram and using then the Newton's laws, like summation of forces along x direction to be equal to m times the acceleration along x directions. So using all those, we were able to find out the differential equation, and that was mass times the acceleration plus b times the velocity plus k times the displacement was equal to the applied force. Now the question that I'm going to raise now, that can we take this equation and transform it into a state space model? And that is very simple scenario. I can say once again, write down this equation like this, that you have, let it be like equation A. This A can be written down like this, that you have mx double dot is equal to minus bx dot minus kx plus f of t, and then you can say that x double dot is going to be equal to minus b over m x dot minus k over m x plus f of t over m. Now with this realization that you have x double dot, I can rewrite this equation to be in terms of v dot, because I know that x double dot is equal to the time rate of change of velocity, which is equal to v dot. So I know that. So in that sense, I will say that this is going to be minus b over m v minus k over m x plus f of t over m. Now I can now see that this particular equation is a first order differential equation. And that was, I've transformed it in this fashion just to make you realize that the state space model was defined to be a model which has got the n first order differential equations. So we have got one of the first order differential equations. But what is the other equation? Actually, when we counted for this velocity, I can say that velocity itself is termed as time rate of change of displacement, and that is going to be x dot. So this means that this equation can be rewritten like x dot to be equal to velocity. So this can be labeled as equation number 1, and this can be labeled as equation number 2, and I can write down in reversing the order, obviously, one first and second later. So that would mean that you can have this whole stuff written down in terms of a set of first order differential equation where you have x dot on one side and you have v dot on the other side. So this is coming from equation number 1, and this is coming from equation number 2. So this is a vector of how the state variables are changing, or state dynamics is equal to. Now I need to construct it in a notation that I've defined earlier, and let me write that one down over there, that x dot to be equal to ax plus b times u. So I need to have this thing structured in this fashion, that you have a multiplied with a vector x, and that would be x and v, because these are these two states in this particular system, added with something like a B matrix multiplied with u, which is in this case f of t. Now I'm going to observe this equation so that I can write down the second row, and I would observe this equation to write down the first row in this state space representation. So let's do that. So x dot is equal to v. So you can see that for that reason it is going to be 0, because 0 multiplied with x time is going to produce 0, and then you have 1 as the coefficient over there, so that when it multiplies with v, it generates equation number 1. And for that, you are going to have, for the f of t, or the input matrix, you are going to have 0 placed over there. Now, considering equation number 2, which I'm going to encapsulate now once again. So that would mean that you have, first of all, minus b over m times v. So v is the second element, so I'm going to write that over there. And it is minus k over mx, so I'm going to write down minus k over m over here. And then you have 1 over m multiplied with f of t, so I'm going to write that one down over there as well. Now you can see, let me use a different color now, just to highlight that you have this as matrix A, this as matrix B, this is, let me use a different color now, this is the state vector x, and this is the input vector u. And that produces the set of first order differential equations that define the state space model. Now the little remaining stuff is what is going to happen with the output equation. And if I can write that one down as well, y is equal to cx plus du was the generic notation. And if I require, in my case, position to be the desired output, so that would be written down like, if x is output, in that case this is going to be x to be equal to 1, 0 times x and v plus nothing added in it. So d is going to be 0, so I'm going to avoid writing that one down. So this is going to be x is equal to c, which is 1, 0 times x vector, the state variable vector, which is x and v in that. So that is going to be your output equation, which is very simply constructed. But if x is not your desired output, rather you are interested in velocity, then you are going to change the c, and that would be like 0, 1 in that sense, and that would produce to the desired output. Now, in this very simple, straightforward example, you can see that you've transformed the differential equation, and I'm going to use a highlighter over there. You have transformed this equation, which is the differential equation, into a state space equation. So this is what you have done from differential equation to state space equation. And that is one of the transformations that we wanted to do. But we have done it in a very simple, straightforward fashion. Now, for this very simple, straightforward system, we constructed the differential equation earlier, and that was this. And we've used this to construct the state space model now in terms of dynamic equation and the output equation over here. Now, at this particular stage, it would be advisable to transform, as we have transformed from differential equation to the state space equation. Can we transform it into a graphical approach? And that can be shown very easily done on this side of the slide. So first of all, I'll consider that you have v dot available, the acceleration available as a signal. And this signal is then integrated. And you have seen the block diagram for the integrator like 1 over s already, which is going to produce v. And if I integrate v once again, I will get x, or the displacement. Now I can see that I can take the v, which is the velocity, and I can see that happening over here multiplied with b over m, and that would be in terms of a block defined like this. And then I'm going to add that to a summing junction. Because you have a negative sign with that, so I'll place a negative sign over there. So it means that you have taken this v signal or velocity from here, and you have multiplied with the transformation b over m, or gain b over m, and then you have added to a summing junction. Now similarly, x can be taken away as a signal, and you are going to multiply with a gain corresponding to this entry, and that is going to be k over m, and that is provided also with a negative sign to the summing junction. Now, which means that you have partially constructed the block diagram. The only thing that is remaining is how you're going to provide something input over here. And that is, you can see that f of t is multiplied with 1 over m. So I'm going to do something like this, that you have a gain 1 over m placed over there, and then you can provide this side with f of t signal. And that is going to produce 1 over m times f of t. Let me use a pointer. 1 over m times f of t on the summing junction, minus k over m into x coming in from this side, and minus b over m times v coming in from this side to produce v dot. And that's the exact expression written down in the second row of this representation. And if you wish to get the output, because in this case x is equal to x is the output required over there, so you can just take this as the output. But if some other transformation is needed at the x, you can obviously add those transformation blocks as well in this block diagram. So in this case, you have transformed from the mathematical representation into a graphical representation. So this is the mathematical representation side, and this is the graphical side that we mentioned earlier. To be precise, it is the block diagram. We still have to see the other aspects of it, but we will explore later on. At this particular stage, I would also raise this question over there that maybe in your case, velocity is not the desired variable. Maybe momentum is a variable that you would be interested in that. So you will slightly modify the same equations to account for that momentum term as well, if that is needed. And we're going to use some other transformations as well in the later discussions, but as a starting exercise, this is just like a very simple, straightforward exercise, which gives you the realization that how differential equations can be transformed into state space models and how state space model can be transformed into a graphical representation, in this case, a block diagram. This is end of part 1, and in part 2, we are going to keep on discussing this topic and discuss all these conversions in much more detail. So please watch that lecture as well.